So when we had categorical data, all we did was we made counts or frequencies in each of the categories. It was already divided out for us. When we have quantitative values, there is no specific, you should break it up like this every single time, way to make piles of the data. So usually what we do is we'll always do, at least as far as I know, equal width bins. And then we'll count the number of cases that fall into each bin. So this is called a histogram. And it's one of the primary ways that we're going to be looking at the distribution of our data. It's nice because it can show you the shape of your data really, really quickly. One of the things we're interested in is the shape of the data. We're going to be interested in the spread of the data, the center. We're interested in any weird things that happen, like gaps. So this one is actually, some of you may recognize it and be like, oh, that looks familiar. Yeah, that's from a 7th grade pre-algebra test. Someone was throwing darts with their left hand at a dartboard and measured the distance from the bullseye in inches and made a histogram out of this. Whoever it is pretty good, but occasionally has some stray shots. Notice that unlike a bar chart, there's no gaps between the bars unless there's a gap in the data. So like on this one, these are all 1.5 apart. Between 10.5 and 12, he had no shots that were that distance from the bullseye. And we can see that because of this gap. So with bar charts, there should always be a gap between the bars. With histograms, you'll only have a gap when you have a gap in the actual data. Notice that this is the frequency. In other words, sometimes we'll write the count over here, same thing. If we did a relative frequency histogram, which would have percentages over here, the scale on this side would change, but the shape of this would not unless we changed the bin width. So on tonight's assignment, part of what you're going to read is about how to use your calculator to make a histogram. And also how to adjust it. One of the things that is interesting is, well, how many bins should you have? If you have too few, your data is all spread out all over the place, or is all bunched up, and you don't really get a sense of the shape. If you have too many, it's too spread out, and you don't get a sense of the shape either. All right, let's move on. So, something that's like a histogram, but keeps the individual scores for us, and we did this again in 7th grade, is a stem and leaf display. Or if you call it a stem and leaf plot, that's fine. Your book calls it a display. I don't really care. I guess the reason that you don't call it a plot is because it's not a graph. A plot is always a graph. So this one, again, I remember this from your pre-algebra book, where they had the weight of each girl on a basketball team, and they showed a stem and leaf display kind of like this. There's a couple of things that are not so nice about the way that this one is done, and I did that on purpose. So we really need a title on this, right? Without the title, can we really get the context of what's going on? Not really. So I'll add that. So something like this, weights of girls on the basketball team. And you should also put in some place what it is this means. So you just pick one that's on there. I usually pick the first one, 10 and then a slash and 6 means 106 pounds. Because at that point, we didn't even know what units they were in. They could have been in kilograms instead. That would be some pretty beefy players, but now sometimes, especially if the numbers are very large, and your book talks about this, I think specifically as it relates to weighing steers, that sometimes it's easier to, let's say you had a steer that weighed 1,468 pounds. They would actually do it like this, and they would just cut off the 8. Because within 10 pounds, it's not all that big a difference. You know, that could be the difference in what he had for breakfast today. So you'll see that, and it would be 146 means 1,460 pounds. The other thing that you will see sometimes is if there are a lot of data values, that they'll do a split. So for example, here they might split up the 120 pounds into 2 different groups. And so in the middle of your chart, you would have 12, 6, and here you'd have a 12, 0, 0, 2. For one that has this few data values, you don't need to split it. But if it has a lot, you will. And your book says, I don't know if you read this up here or not, but it says they're useful when you make them by hand for batches of fewer than a few hundred data values. Yeah, I'm unlikely to do a few hundred data values with a stem and leaf plot by hand. It just gets kind of ridiculous looking. One other thing to notice is that with this one, since I have the smaller values at the top and the larger values at the bottom, if we were to rotate this 90 degrees counterclockwise and draw the appropriately sized bins around them, you have a histogram. Now, most of the time that you'll see these in your book, they almost always do the larger values on top and then the smaller values on bottom. So if you could rotate it, but then you have to flip it over to get what the histogram would look like. Any questions about that? This is really a lot less fun than being there in person. I've got to tell you. All right. So the next one we're going to look at is one that we have not done before, is a dot plot. A dot plot just places a dot along an axis for each case of the data. Again, one of the nice things about a dot plot is it doesn't lose any of the data. A histogram, we lose the individual data points. The nice thing about it is it gives us a good picture of the shape of the distribution, but it loses individuals. So this doesn't group the data into bins like a histogram does. And sometimes it's great and sometimes it's awful. It just depends on how many you have and how spread out they are. So this particular one was for fuel economy for a random sample of 2015 model year vehicles. Uh-oh. We lost somebody. We lost Ian. He's still there. um, so these can be nice. This shows you kind of how spread out it is, but there aren't any groups. Okay. Now, for these three types, histogram, stem and leaf display, and box plots, you have to have quantitative variables. If you have qualitative variables, we need to use either a bar graph or a segmented bar graph or a pie graph or a pie chart. One of those would be best. Any questions about that first page? Okay, let's go on to page 2 then. The shape of a distribution. Again, this should be somewhat of a review for you. We talked about this at least some in 7th grade. And some of you I know weren't here in my 7th grade class, so that's fine. We're going to go through it as if it's all brand new to everybody. First of all, the shape. There's a couple things we look at. This one, notice it has this strong high point that's higher than everything else around it. That's called unimodal. Una meaning single. It has one mode. With this one, notice we have these two different humps. And this one always cracks me up because, well, frankly, it looks like two different people shooting the bird at the same other person. This is bimodal. You have these two humps on this one. And when we talk about modal, we're not saying that the mode has two different values, because the mode can't have two different values unless they're exactly the same. But here we're saying it's bimodal in that there are two high points on the graph. And then this one is multimodal. It's got all kinds of high points and then low points. Okay. If it doesn't have any obvious mode at all, like all the bars are about the same height, look down here at the bottom of your page over here. That's called uniform. And is it perfectly uniform? No, we're not saying it's perfectly uniform. We're saying the shape is basically uniform. All right, next thing is the histogram symmetric? In other words, could you draw a vertical line? So something like this. And if you fold it in half along that vertical line, are the two sides basically the same? Okay, they don't have to be perfectly the same, but are they basically the same? This is symmetric. And again, I took this one from Wikipedia because I was like, oh, that's interesting. It's not at all close to being perfectly symmetric, but it's pretty close to being symmetric. Okay, this particular one is unimodal. You can have symmetric data that's bimodal or multimodal, but it's a lot less common. You just won't see it nearly as often. Now, this part out here on the far left and on the far right, which is usually shorter than everything else, those are called the tails. So this is the left tail, and this is the right tail. Now, if you have certain data types, you're going to find that the data is skewed to one side or the other. So take, for example, this one, and I know that that's kind of hard to read, but this is yearly income in thousands of dollars, and this is the relative frequency of that happening. And so these are decimals that we could change into percentages. And notice that there are, this is unimodal. It has one really high point, and then it just starts dropping off. And you have a long tail on the right side. This is right skewed. And there are a lot of distributions that you can find that are going to be right skewed. where most of the data is in here, but then there are some that are way bigger than everything else. I will say I used to do these backwards. I used to think that this was left skewed and this was right skewed because I thought it was where the data was, but it's actually where the tail is. So be careful not to get those mixed up. Right skewed is which way is the tail pointing? Points to the right. This one, I think when I found this one, it talked about what it was, but it didn't have it labeled on the chart. Anyone want to hazard a guess for what the horizontal and vertical axes are measuring? Percentages of, okay. Yeah, that is a good guess. I want you to notice on this that it is very much left skewed, but it has this one high point in here down at the bottom. What kind of a thing might have that? And this is something where I wouldn't expect everyone to immediately jump to it. Okay, no one's going to take a shot. This is age at death. And this was the frequency. So, although it has nothing to do with what we're talking about, what's going on here? If we were talking about, go ahead. Yeah, this is infant mortality rate, which if you're studying, different countries and you're looking at their health overall, how developed they are as a nation, um, the less developed, the higher the infant mortality rate tends to be. Okay, more developed, more prosperous, richer nations tend to have a lower frequency of infant deaths. Although even in those, it tends to be. I don't think it's this much higher, but I think it's higher than the next several years. Okay, once upon a time, the infant mortality rate was probably way up where there were times where, sometimes, have you guys ever looked at something that says that the average lifespan was about 30 years or something? Yeah, it's a deceiving statistic. The reason why the average lifespan was so low wasn't because 30-year-olds were croaking. It was because they had a high infant mortality rate. People still generally live 60, 70 years, but they had a high infant mortality rate, which brought the average way down. So it wasn't like during that time span that you were surprised if you made it to 40 years old. There were plenty of people who were older than that. Okay. All right. Thus into the, I don't know what kind of lesson that would be. Okay. So here's some more. These are also out of your seventh grade textbook. This is symmetric. This is what kind of mode would you say this was? I don't know if I'd go multi, although, you might be able to twist my arm and make me say that. I'd probably say bimodal. When we're talking about bimodal or something, they don't have to stick up way above everything else to be bimodal. They just have to be, I have a peak here and a peak here. So this one's skewed, and what else? Yep, unimodal. Some textbooks call this single peaked, but I would call it unimodal. Same thing here with double peaked. I would call that bimodal. And we've already looked at uniform. And when you think about uniform, again, it doesn't have to be perfectly uniform. For example, all of you are wearing a school uniform, but not everybody is dressed exactly alike. Okay. All right. Any questions about this page? Okay. Let's move on then. So we're still looking at the shape. And one of the things we might want to know is, are there any unusual features that stick out? So if you're describing the distribution, one thing you should always mention is, are there any potential outliers? So like on this one is way away from the rest of the data. It is likely an outlier, although our scale isn't very big. Notice that's 60.0 and this is 61.2 all the way over here, and this is 64.8. So we will come up with some rules of thumb for what we consider to be an outlier a little bit later. But this one, pretty much I would go, yeah, I think that's an outlier, even though this data doesn't have a lot of variation. Now, with outliers, the deal about them is sometimes they're going to tell an interesting story about your data. How did I get to have this particular outlier? Sometimes it's going to be a mistake. Sometimes an outlier is one where somebody dropped a decimal place or inverted two of the numbers or something like that. So you never throw away something that appears to be an outlier without commenting on it. If you're sure that it's a mistake, frequently it's like, yeah, that can't be. No one high jumped 75.3 feet. So we can safely throw that away, but you would still report it. And sometimes it's like, yeah, that was someone who was shot out of a cannon. I don't know. Now with an outlier, there'll always be a gap, but gaps can happen when there are not outliers. Like on this one, maybe this is an outlier, maybe it's not. Okay, we would have to look at some other things to determine whether it's an outlier or not. So that's shape. So for shape, you're going to look at, is it unimodal, bimodal, uniform, multimodal? Is it skewed left? Is it skewed right? Is it symmetric? And then you'll also look for any unusual features. Okay, then we're going to look at center and spread. Now, we did this in pre-algebra also. The middle value that divides the histogram into two equal areas is the median. The median is going to have the same units as the data. And you know how to find the data. You put all the values in order, either from least to greatest or greatest to least. Most people like least to greatest, but it's not important. And then finding the middle number if there's an odd number of values, or by averaging the two middle values if there's an even number of values. All of you have done that before. I'm not going to spend any time on it. And then the spread, there's a couple of different kinds of spread that we're interested in. One is the range. And unfortunately, in common use, people say range and they give it ranged from 10 to 500. Well, that's not actually the range. And if you said that it ranged with a D on the end of it, it's okay to say it that way. But if we ask for the range, it's a single value. So if it ranged from 10 to 500, the range would be 490. Now, one of the problems that we have with the range is that if you have an outlier on either side, it can make it seem like the data is way more spread out than it actually is. So what we would do is talk about the middle half of the data. So we divide the data in half, with one group consisting of numbers above the mean and the other, not the mean. That's the wrong word. What should that be? Try again. Median. And I did it. I doubled down halfway through. This should also be median. My apologies. And then divide those groups in half again. Again, we did this in pre-algebra. Do you remember what the mean of the lower half of the data is called? Very nice. The first quartile or quartile 1, either way is fine. We usually use Q1 for that. And the mean of the upper half of the data is called the third quartile. Some books call it the upper quartile. Either one is fine. And we use Q3 for that. Does anyone remember what that's called when we take the difference between those two? It's only been 2 years, guys. What if I give you the abbreviation? IQR. Yes, it's the interquartile range. So the nice thing about the interquartile range is that it's not affected nearly as much by any outliers. So it tells you about, in the middle of my data, how spread out is it? So it can tell you how compact that is. I feel like I'm missing things because people are laughing and we should just leave one person's mic on all the time so that I'm not feeling like I'm teaching in a vacuum here. That would be fine. Yeah, why don't we do that tomorrow and see how it works? Okay. So the one exception to using this is that if you have strongly bimodal data. Most of the time when you have strongly bimodal data, you probably have two different groups. Not always, but probably have two different groups. And they should have been analyzed separately. For example, if we were doing heights of students, you probably would have one spike near the average height of the guys and one spike near the average height of the girls. So that would be a bimodal distribution because you have two different groups that have actually different characteristics. So moving on, the 5-number summary is the median, the minimum, the maximum, quartile 1 and quartile 3. With this, it's also a good idea to include the number of data values and the identity of the cases. So here, this is a 5-number summary for the run times in minutes of the 150 highest grossing movies of the year 2010. So of those, the minimum was 43 minutes. That's incredibly short. 160, that's 2 hours, 40 minutes. That's like Lord of the Rings territory there. And the median is about 1 hour and 45 minutes. I usually think if a movie is shorter than 90 minutes, then it's not really like a full-length movie. That's just in my own head. And that would put it in the bottom quartile. All right. So what can we do with those? Well, we can draw a box plot. And you guys did box plots, again, in pre-algebra. We're going to do them slightly differently in this, but not a lot. Your book likes to draw vertical box plots, which I don't care for, but it's fine either way. So here are the steps. The one thing that's going to be different is we're going to draw fences around the main part of the data. The upper fence is going to be 1.5 IQRs to the right of the upper quartile, and the lower fence will be 1.5 IQRs to the left of the lower quartile. They're not part of the display, and so you really should erase them after you do step 4. So here is a histogram, and this was the number of days that the average wind speed was a particular value. Notice very sharply, very strongly right skewed. It's unimodal. And what we would do if we had all of the data is you would first mark the median, which was 1.12. We'd mark the upper quartile and the lower quartile. The upper quartile is 2.28, that's here. The lower quartile is here at 0.46, and that's all exactly like you would have done in pre-algebra. Nothing has changed. But then what you would do is figure out where your fences go. So your fences on this one, you first have to figure out, well, what is the interquartile range? So for this, that's going to be 2.28 minus 0.46. So 2.28 minus 0.46 is 1.82. So our lower fence is going to be quartile 1, 0.46, minus 1.5 times the interquartile range. So that's 0.46 minus 1.5 times 1.82 is negative 2.27. So I usually draw them with a dotted line, because I'm going to erase them eventually. Your lower fence is way over here. And then your upper fence is going to be quartile 3, 2.28 plus 1.5 times 1.82. So 2.28 plus 1.5 times 1.82 is 5.01, which is right about in here. So then what we'll do is we'll draw lines from the end of the box to the right and the left to the most extreme values found within the fences. Well, obviously there wasn't going to be anything over here because you can't have negative wind speed. So there must have been a day when there was 0. And it looks like there was a day where it was about 5, maybe less. If it's exactly at the fence, you can draw it all the way to the fence. If it's more than the fence, then we're going to mark those as being outliers. So that's kind of a rule of thumb for outliers. If it's more than 1.5 IQRs above Q3 or 1.5 IQRs below Q1, then we consider those to be outliers. And again, that's a rule of thumb. Your book talks about this some. There are several different rules of thumb for what's an outlier and what's not. But we'll use this for box plots. And then you go back in and you erase the fences because the fences are not actually part of your display. Notice on this, most of you probably would have immediately realized that this one value was an outlier. It's less likely that you would have noticed that these are considered outliers also because they're so close to these other parts. Okay, any questions about that? All right, we will leave the rest of this for tomorrow, but right now let's do the quiz. I'm assuming Mr. Wheatstruck asked someone to go get him when it was time for the quiz. There goes Andrew.